All right, so welcome everyone. I'm Tom Beckmann from the Software Architecture Group. We have three topics of focus, one being virtual machines, programming languages, and finally development tools. And today's talk will be in this area, mainly in the area of development tools, but also with some overlap over to the programming languages. So in the title, you've seen no code, no limit, and something about block-based. But let's first talk about this term of no code, specifically our understanding of it and how we'll use it throughout this talk. So we are seeing no code as a form of high-level abstractions for programmable behavior, data, or configuration. So any user interfaces or other forms that manage to lift the abstraction level so high that we might not code. What does this look like at the moment? Well, most of the time we observe that no code is realized in a manner that we receive a user interface that builds on top of an inaccessible low-level host language, maybe through some form of code generation or something like that. But what we may actually want to have are domain-specific abstractions for our task at hand and tooling that works across layers such that we can go down the layers if we need to and pick the right tools for the right job, which may sometimes just be actual code. So let's talk about block-based for a moment. And if you've just attended Jens Möhning's talk, you will probably already be quite convinced of its capabilities. For one, its structure supports composing domain-specific visual abstractions. So if you have a look at the example here on the bottom left, we have this little LED display where we can just kind of insert or encode this idea of this display inside our blocks. And similarly, the way that the palettes, these block libraries and blocks work, can support us in working with less frequently used languages where we might have to remember, recall certain things, discover things in new, maybe for the first time, maybe again after not having used something for a longer while. While these things are for sure great benefits, there are also some limitations if you consider block-based programming for larger projects. For one, by design, they are meant for smaller APIs. So they are made to be discoverable and have the entire API surface accessible in this palette. They are mostly designed for mouse-driven interactions, which of course might slow some things down. And programs tend to consume considerable screen estate, even when they're smaller, which of course doesn't matter most of the time because Snap projects are inherently meant to be small and just very expressive. But as we scale to programs with multiple thousands of lines of code, this may not work as well anymore. And the last point here that I mentioned is the integration with the host environment and existing infrastructure might be a challenge as well, depending on how exactly you're realizing your block-based environment. So deriving from this, we have two questions. For one, if we think in these visual abstractions, what novel workflows could these potentially facilitate? And second, maybe more of a prerequisite, how can we scale block-based programming to professional workflows? Even though I personally find the first question a little more interesting, the second one is, as I said, a sort of prerequisite in my opinion. So this is also the one that we want to talk on, that we want to focus on as part of this talk. What you'll see in a moment is the demo of a block-based programming environment that we are currently prototyping. Its goal being exactly to answer this second question. We want to support the workflows of professional programmers in a block-based environment. And professional, for this case, means large projects, so thousands of lines of code and debugging tools, and whatever else you may be familiar with, so version control, etc. The prototype in particular supports multiple languages, mainly Smalltalk and Scheme right now, and a subset of JavaScript. It does integrate with file-based editing, so you could, in theory, just drop it onto your regular source project. And it is written in the Squeak Smalltalk environment and has been used on at least one large project, namely itself, which is clocking in at around about 40,000 lines of code at the moment. All right, so let's consider the demo. So I'm in the editor right now, and I can access the classes of the host system using this little code opener widget over here. So these are essentially all the things that I get from my Smalltalk environment. And let's jump specifically to our demo. Exactly. And you can see here I have these couple of classes that constitute a card game. I have a card class, I have a game class, I have a player class, and I also have a little test. So just to see what it looks, I have a little example here that I can open up, and if I just run it, you can see we have this basic game popping up. And the way it works is that we have two players, each with some cards on their hands, some card on the board. And if I play a card, they cause a special effect, and the default cards effect is just to remove the lowest cards of the opponent. So you can see each card has an attack value and a defense value. So if I play a card now, it will remove a card accordingly. So this looks kind of blunt at the moment. So let's try and spice it up a little. Each card has a draw function that I can open up here. And you will notice that the code presents itself in a very text-like manner. However, it is actually already, in a sense, blocks, in the sense that I am mapping the actual abstract syntax tree onto my blocks. But if we consider the case of a programming novice here right now, this may appear a little daunting already. So in order to make it a bit more approachable, we have different options. For one, we can also use a palette that I can open here on the right, and I can switch to a maybe more friendly layout of the blocks that might remind you of Scratch or Snap. So we can already tell the color that we are wanting to change to make the cards look a bit more fancy. Might be this one over here, considering this same color blob is over here. And you'll notice that it is actually presented as a color in our source code, which is because we are sort of abstracting of this idea of a color constructor to an actual color picker. You can also instruct the environment to change that by using this little convert button and displaying it as small talk again. And you can see here what is hidden behind it, namely this color constructor with three different RGB values, of course. So let's go back to the color picker and let's see what we have in the palette. You will notice when I switch between the two programs that on the left-hand side here, there's something new appearing, the canvas section, which is specifically made for all sorts of functions that act or have access to a canvas. So if we drop down here to styles, you'll notice that we have a gradient here that I can just drag and drop over here and drop into our code. And if I save that, you can see it is already applied, just not maybe with the prettiest of colors. So let's adapt that real quick to something that is a little more pleasant, maybe like this. All right. So this was the first change we wanted to do. Next, we have this little freeze card over here. If I play this, the defense values of my opponent's cards will be decreased by 5. So these numbers down here will all go down if I click this now. Some of them dropping down to the negatives, which is exactly what we don't want. If this happens, we want the cards to be discarded instead. So we have a test for this very behavior. Let's open that up. You can already see it's getting kind of crowded in here. So let's switch to a display of the blocks that is a little more concise. The draw-on function we don't need anymore, so we'll close that up. And now we can see the test here. The way that the blocks are displayed now is to save as much space as possible while still conveying nesting in a manner that is as clear as we can make it through the use of contrast of colors. So if I just save the test now, you can see that it executes and is currently green as it's documenting the current behavior. But what we actually want to do now is adjust this test to reflect the new desired behavior. You can see here that similar to the colors, we are now from our domain, the specific representation used in the code here that I can again convert to Smalltalk, and you can see it's just another constructor of this little card behind here, just did more familiar, and I can just copy paste this to catch one of the corner cases, namely that the defense is exactly 5, just to make sure that we're catching that right. So the behavior that we want to have later on is that this card gets deleted, and this card over here, I'm just copying and pasting it down here, gets dropped to a defense value of 0. You can see now that our test is failing, and I can also open it in the debugger here to see the failure. But in this case, the debugger doesn't actually just an assertion that's failing. So what might be of more help here is to place a watch on this expression, which actually renders out what player 2 has on their board after our player 1 played the freeze card that I mentioned here. So just to walk through this again, we are initializing player 2's board with these 3 cards. We're playing our freeze card, And then we're looking at the board, asserting that it has this exact structure, but currently it ends up with the structure, which is, as per our new definition of the game, faulty. So let's try and address this by opening the build freeze card, which I can just do by getting the implementers of this function. And there we go. You can see here that it is rather concise again, and that we're actually using a different language to express the logic used for the effects, which we could maybe imagine to be some sort of scripting interface to make it easier for our users to adapt effects without having to learn this full-blown host language that is Smalltalk, and instead being able to rely on this maybe a little simpler scheme language. So if I click in here, you will notice that our palette changes yet again to adapt to the language that we are now in particular that it also has a couple of utility functions down here specifically for our card game. So our intent here is that after all the cards have been weakened by 5 values, to look at all the cards that dropped into the negatives and remove those. If you look down here, we do indeed find that we have a remove cards function. So let's drop that over here. And it asks us for a player. So let's take the opponent from our Smalltalk environment and drop it onto the scheme variable, which now creates a binding over here. Since we want to do that after the filtering has been done, let's move that down here. And the last thing that we need to do is provide this list of cards that is actually to be removed. How will we go about this? Well, if you've worked with Scheme before, you will know that there's a filter function that we can use to filter out the cards that have a value of below 0 in this case. So let's take the less than operator, get our cards defense. There's operator over here. We want to compare that with 0. We want to apply it to a certain list, in which case, namely, which we already did once over here. So I can just copy paste that over here. And yep, if I execute this test right now, you can see that we're green. The cards are indeed as they are, should be, as we can see here from the watch that confirms that our elements in the actual runtime are identical to what we expected. So let's close these up and do one more feature. We want to make sure that players have feel a certain sense of pressure when they're playing the game. So we're going to add a time limit to how long they can take their turns. Fortunately, we already have a state machine governing whose player's turn it is. So let's open that up. And I'm just going to convert it quickly to Smalltalk again so you can see what's happening under the hood. You can see here that we have an actual declaration of the state machine, but this goes beyond what we've seen so far because it actually mixes in other behavior as well. We have like these blocks that add certain triggers to what is actually happening. But let's switch back to the state machine editor. You can see here that we have 2 different states for the different players' turns. And when the signal arrives that either of the player played, we toggle between the 2 states. So luckily, again, our palette offers some extensions for this specific thing. And fortunately, we even already have a concept of time-based transitions. So we can just drag and drop this thing on here. That's me, yep. And maybe put this to 2 seconds, copy, paste this guy, put it here. And if I now save the code, you will notice that on the left-hand side, the game now starts toggling between the states. Since this is now a duplicated constant, we can also use our refactoring tools inside of the state machine to maybe call this variable turn time out. So you can see here now I created a new function. Oh, let's move this up here. And I can actually reuse this over here now, save that, maybe drop this down to 0.25 seconds. And now you can see that our players will have to think a lot quicker. All right, so now I've added my new changes and how to actually get them out of the system. Well, in the end, we can choose a different representation of the same thing. So if I now go into my Git integration over here and just create a new commit, you can see that all our changes that we just created are actually down here, and we can just kind of type freeze effect improved or whatever and create a commit ready to be pushed. All right, so this was the demo. What we just saw were that we were able to use different projections for both views and interactions, depending on the level of abstraction and complexity we wanted to deal with. We saw that we had support for multiple and parts domain-specific languages or abstractions to work with, and that we were able to integrate with parts of our infrastructure, such as debuggers. So there were two things that were maybe not as clear in the demo. One of them being how we are actually able to extend this block-based interactions that we might be used to keyboards. So you've seen that I was able to use blocks in this maybe familiar manner of drag and drop that you've seen in other editors as well. But we actually extended this to keyboard, and you've seen me use the keyboard on a couple of occasions during the demo, but not as much. But how this works is that we're actually not constraining ourselves to just the palettes, but we can also just type in a new identifiers from our API surface. So if I have a piece of JavaScript here, I can just type pass.join, and it will just appear as I expect it to. To make this viable, we're employing a system of grammar-assisted input, or rather that we call grammar-assisted input, that is inspired by the grammar cell system that is found in MPS. So the basic idea of this is that whenever we receive an input that is not valid for the current block, we try to interpret this as the intent of the user to perform some type of tree transformation. So if we start here with this unknown block that is just this empty hole waiting for us to fill, and we want to create this a.join expression in JavaScript, which in terms of its syntax tree resembles this expression here. So the invocation at the top, and then this refers to this operand over here, this a.join. So if the user types an a, this will just convert this block that was waiting for input to be an identifier node. If we now type a dot, this is not a valid input for an identifier, so we can identify this as the intent of the user to perform a tree transformation where the dot is taking the a as an operand. If the user now types a j, this is again not valid for the dot operand or for infix operands more generally, so we can move this to the waiting operand on the right-hand side, allowing the user to just kind of finish out the identifier. And then they will press, as you usually would, the opening parentheses, which by default would just kind of get wrapped onto the current block, similar to how it happened here. But this is, of course, not actually what we want if we are typing out actual proper JavaScript, because we have to consider the precedence rules. In this case, we have two nodes with the same precedence, but they are left associative, namely the dot operator and the parentheses operator. And we can fix this by left rotating the subtree, taking the new node as the pivot, ending up with this structure where the parentheses are ordered at the very top and the operand ordered below. So as the user types in the expressions just as they would in normal JavaScript, we are able to reshuffle the tree to adapt to these changes. We actually did a theoretical evaluation of our keyboard-based system in two scenarios where we kind of simulated what might be considered perfect input, just like taking the tools provided by different editors, normal text editor, the Vim editor, and our editor. And we found that at least for these two editing tasks and on a theoretical level, again, we are maybe managing to even beat Vim by about 10% of keystrokes. But this is, of course, preliminary and will have to be evaluated further with other users, but demonstrates that we're at least able to reach a comparable level of input efficiency here. So the second part is the question, how do we actually get a programming language inside our blocks? The JavaScript parser Babel lists around 90 different types of nodes, which we could, of course, just translate into the blocks that we want to have. But this would lock users into a certain choice, make them lose flexibility in terms of what they can actually do and how they have to decide what type of thing they want to actually have, and not just like be flexible as you can be with text, changing a plus to a minus, etc. So what we do instead is we try to summarize aggressively what types of block we find. For one, we have prefix operators, so anything that comes before another thing. We have infix operators, so anything that comes between other things, where we even include things such as the method call. We have blocks, so any keyword followed by some type of block structure. And in the end, we also have literals, the various things that you need as the leaf nodes here. So what does this bring as an advantage? Well, the user can convert directly between structurally similar blocks. So I'm just changing an if to a while or even to a function, and we can easily accommodate this change because it's just one type of block, one type of idea that we have to convert between. But we also at the same time not limiting our language implementation, as it is able to specialize the exact behavior of the block through strategies. So if we swap out an if for a function, behind the scenes, the logic adapts on what it might mean for the environment or the IDE, that this block has now taken on a different semantic, but the user just sees another block that represents a JavaScript block statement. So yeah, what's next for this editor? For one, the languages that we are mapping right now are comparatively simple languages that don't have as much syntax compared to some of the more intense languages such as Scala or C++. So that is something that we want to check out in more detail. And we want to explore further visual primitives and projections for general purpose programming, such as this demonstration here from other authors here that mapped the concept of tree transformation onto a graphical level, allowing us to use pattern matching to express certain aspects of algorithms. So yeah, this was the talk. I demonstrated that we were able to use and to provide stronger abstractions in our programming environment by using a fine-grained composition of languages and tools. And by saying fine-grained, I mean down to the level of individual expressions and even nested in one another. We were able to demonstrate that we can extend the current direct manipulation, CADA-based workflows of block-based editors to keyboard-driven workflow through things such as our grammar-assisted input. And finally, we are able to scale to large projects by compacting the display as much as possible and integrating with the infrastructure and tools that are already provided by other projects. So thank you very much for your attention, and this concludes the talk.